Good evening, sir. Today we will be presenting our PPT on centrifugal pumps. So with me are my friends Snehal, who is roll number 2K20 ME272, Saurabh Sonkar 2K20 ME276, Siddharth Sahu 2K20 ME271, Somnath 2K20 ME273, Saurabh Banwal 2K20 ME275, Siddharth Kumar Jha 2K20 ME270, and me myself, Saurabh Bansal 2K20 ME 274. So moving on to the index, the things which we'll be discussing about in this PPT. So first we will discussing about the introduction and the components of a centrifugal pump, and then we will be discussing about the velocity triangle, and then characteristics of centrifugal pump, axial flow pump, then cavitation, then effect of viscosity, moving forward to pump and system characteristics, and at the end matching of pump and system characteristics. So uh, moving to the introduction. So a pump is a device that transfers energy to aid transportation of a liquid from one location to another. So a typical example is the pumping of water from a well or a sump to an overhead reservoir. Another related use of pumps is to circulate a liquid in a closed system. So yeah, typical examples of this could be the circulation of cooling waters in machines and circulation of lubricating oil to various moving parts of a machine. So there is a vast use of pumps, and therefore there are various sizes of and shapes of pumps that are widely used in households and industries. So basically there are types of pumps, which and the first type is rotodynamic or centrifugal pump, and another type is uh, positive displacement pumps. So there are different types of centrifugal pumps as well, which are pure centrifugal, mixed flow, axial flow. There are different types of positive displacement pumps as well, which are reciprocating and rotary, and miscellaneous pumps as well. So we're discussing in brief about positive displacement pumps and in detail about centrifugal pumps. So moving forward to the positive displacement pumps. So positive displacement pumps transfers captive volume of liquid successively through action of a device such as piston, vane, screw, etc. in a closed chamber. This class of pump works on principles of physics that are neither of pure rotodynamic type nor of the pure positive displacement type. Positive displacement pumps are designed to ensure that any pumping action is forward. Its internal design ensures and prevents fluid from recirculating back towards the pump inlet or within its casing. So now discussing about the rotodynamic or centrifugal pumps, we will be discussing more about it in detail in the further slides as well. Here is a brief introduction about it. So in a rotodynamic type of pump, also called as dynamic pump, a rotary element known as impeller imparts energy to the liquid. So the impeller itself is driven by a prime mover, electric motor, IC engine, or steam engine. So the kinetic energy of the specially designed rotating impeller is transferred to the liquid in terms of pressure energy and kinetic energy, and the differential pressure causes the liquid to flow out to the delivery point. So the centrifugal pumps are popularly also known as rotodynamic pumps and rotary or dynamic pumps, and and are used in many industrial applications. So nearly 75% of the pumps installed in industries are of centrifugal type. So yeah, so moving on to the components of centrifugal pump. So first it is the impeller. So and an impeller is the equivalent of a rotor in a turbine. So it is the main rotating component and consists of an assembly of a set of curved blades mounted on the main shaft. The shaft is driven by a prime mover, which in usual cases will be an electric motor or IC engine. It is the opposite of a turbine, which extracts energy, which extracts energy, uh, from a motor and reduces the pressure of a flowing fluid. There are usually three types of impellers used. So first one is the shrouded or fully enclosed impeller. So shrouded or fully enclosed impellers are the most common type, and in this the blades are covered on both sides by shrouds. Shrouds are the cover plates. So the impeller is uh, essentially a set of two circular discs sandwiching the blades between them. One of the uh, discs are also called as shrouds, has a circular coaxial opening in the center to provide inlet to the liquid, and the other disc or the shroud is solid and has a connection on the outer side to the driving shaft. The flow from the suction pipe enters through the central circular opening and then moves radially outwards and ejected at the periphery of the impeller. So this type of impeller gives better guidance to the liquid in its passage through the impeller. So also there is no slippage of the liquid, and that is acted upon the by the impeller. Also the shrouded impellers are only used for clear liquids. So the clear liquids are those liquid which do not have suspended solids. So moving forward to the semi enclosed impellers. So this type of impellers has a shroud on only one side. That one side is connected to the shaft. So this type of impeller is used when the liquid to be pumped contains some solids in suspension, unlike that of a fully enclosed. So the absence of one shroud gives some leeway for the solids to negotiate the path from the inlet to outlet through the impeller and prevents clogging of impeller passages. So semi-open impellers only have a back wall that adds strength to the impeller. This is the diagram depicting the semi-enclosed impeller. Moving forward to the fully open impeller. So in this type, the blade assembly is open in the sense that there are no shrouds. This type of open impeller is meant to handle highly solid leaden liquids like concrete, slurry, sewage, and water containing sand and silt. They are also good for handling highly viscous liquids. So to provide strength to the blade assembly, ribs or partial shrouds are sometimes used, and the liquid slippage in the clearances between the casing and the impeller is a possibility in these kind of impellers. So moving forward to the different uh, uh, category, different components of centrifugal pump. Second one is the casing. So talking about casing, so the pump casing houses the impeller assembly in an airtight chamber. The casing includes suction and delivery openings and arrangements for the drive shaft to be connected to the impeller. The space between the impeller and the inside boundary of the casing is shaped to provide a diffuser for the flow emanating from the impeller. So, this is to convert a considerable part of the kinetic energy of the flow that comes out of the impeller into pressure energy, and thereby reducing friction and other losses. So there are different types of casing as well. First one is the volute casing. In this, the impeller discharges into a spiral form of casing known as volute casing. So the cross section area of the volute is least at the junction with the outlet pipe, which is known as the tongue, and gradually increases towards the delivery pipe exit. The idea behind having this shape is to keep the velocity of flow constant at any cross section, This unit is like the reverse of the spiral chamber in a reaction turbine. Volute casings are very widely used in single stage centrifugal pumps. So yeah, and also a centrifugal pump with volute casing is also known as volute pump. So that's about volute casing. Moving forward to the double volute casing. So usually in high capacity, high head centrifugal pumps, the shape of a single volute chamber causes substantial unbalanced radial forces on the shaft. So in order to overcome this problem, double volute casing was developed. So in this, a divide is a divide partition is made so that it divides it into two parts. The radial forces on the shaft are balanced. So this means smaller shaft sizes and reduction in bearing costs. At the same time, the main purpose of the volute in acting as a gradual diffuser of the velocity is also achieved. Moving forward to the turbine pump. Uh, So in this, a casing in which a stationary set of guide vanes are provided to diffuse the flow of the impeller on its way to the outlet, which is known as turbine type casing. This casing is usually circular in cross section and concentric with the impeller. Centrifugal pumps of this kind are sometimes called turbine pumps. Guide vanes are employed in almost all multi-stage pumps, while volute casings are extensively adopted in single-stage pumps only. Moving forward and discussing about suction pipe with strainer and foot valve. So the suction pipe denotes the pipe leading from the intake to the pump. If the intake is a sump situated below the level of the pump, the suction pipe will be subjected to vacuum pressures, and hence airtight fittings are a necessity. At the end of the suction pipe, a strainer is fitted to prevent debris from choking the suction pipe inlet. Further, a non-return foot valve is fitted at the downstream end of the suction pipe to prevent the suction pipe draining out when the pump is stopped. Also, the foot valve helps in priming of the pump. And now discussing about the delivery pipe with control valve. So the pipe that carries the liquid from the pump to its destination is known as the delivery pipe. In the delivery pipe adjacent to the pump, a control valve, which is usually known as delivery valve, is provided for purposes of regulating the flow. All centrifugal pumps are started with the delivery valve in closed position. Further, before stopping the pump, the delivery pipe is closed first and then the pump is stopped. This operation is to prevent possible backflow from the delivery pipe and consequent damage to the pump. So yeah, that's it from my side. Now my friend Snehal will be discussing about the velocity triangle and Euler head of centrifugal pumps. So over to you, Snehal.
Good morning. My name is Nehal Yadav, roll number 2K20 ME272, and I'll be talking about the velocity triangle and the analysis of Euler's equation in centrifugal pumps. So first of all, velocity triangle and Euler head of centrifugal pumps. So for we have the velocity profiles of a blade, of a jet which is pushing towards the blade in a centrifugal pump, and this is the inlet velocity triangle and the outlet velocity triangle. Here, the indications we have are v1 and v2, which are the absolute velocity at inlet, u1 and u2, which are the tangential velocity of the inner periphery and outer periphery respectively, vr1 and vr2, which are the relative velocity at inlet and outlet, alpha 1 and alpha 2, which are the angle made by the vector v and u, and beta 1 and beta 2, which are the vane angles. So first of all, as v1 is the entry absolute velocity at the inlet, so the tangential velocity would be u1 on the right, and just like that, because v1 and u1 are in this position, the relative velocity vr1 will be in this direction, So as the water moves from this direction to this direction, the outlet velocity will be towards this direction, VR2, and similarly V2 and U2 would also show up. V2 over here being the absolute velocity at outlet, and U2 being the tangential velocity. Here, VU2 and VU1 are the world velocity. So, in this case, where the alpha is less than 90, here we will have the similar case where VW1 and VW2 will be smaller than U2 and U1. But um, if the alpha is equal to 90 degree, then V1 and VF1 would kind of merge together, and VW1 will be equal to 0. So that would make V1 equal to VF1. Similarly, in the case of outlet. So the next one is VF1 and VF2, which are the flow velocity. Those are the the vertical component of V1 and U1, and VW1 and VW2 are the vertical components. So the energy head over here is He is equal to 1 by G of VU2 U2 minus VU1 U1. The Euler head for practical use that we use is He is equal to VU2 U2 by G. Now, the analysis based on Euler's equation. First is the static head. So, static head refers to the vertical distance from the water level of the sump to the water level of the receiving reservoir on the delivery side as shown in this figure below. So, the static head H stat is made up of static suction lift Hs and static delivery lift Hd, which is shown as H stat is equal to Hs plus Hd. The static suction head is the vertical distance in feet from the center line of the pump to the free level of the liquid to be pumped, and thus the static head represents the total vertical height, and hence the change in the datum heads to be accomplished in the pumping of the liquid. Next is the Euler head of a pump. So Euler head He is the energy per unit weight of liquid supplied by the impeller in the pump, and it is thus the work done by the impeller per second on unit weight of the liquid. So by considering the radial entry at the inlet, the Euler head is represented as He is equal to VU2 U2 by G. And if there were no losses, He would represent the total lift from the sump that could be achieved by the pump. So that is why this is also called the theoretical head, as certain basic assumptions such as non-existence of circulatory flow and absence of energy losses are made in its derivation. The Euler head can thus be defined as the theoretical head of a pump with an infinite number of blades and total absence of any loss, hydraulic or mechanical, in the system. Next is the manometric head. So the manometric head HM is the actual total head that could be achieved by the pump, and it is smaller than the Euler head He by an extent of HFI, which would make the formula HM is equal to He minus HFI. So these losses are known as hydraulic losses, and they include the fluid friction losses in the blade passage, the circulatory flow between the blades due to the finite number of blades in the impeller, and the shock losses at the entrance. So the ratio of manometric head to Euler head is known as manometric efficiency, and the formula is given below. So there is one case where we apply the Bernoulli's theorem to this formula and to the manometric head formula, which would give us the formula given below. Hs plus Hd plus Hfs plus Hfd will be equal to the static head plus the losses, whatever I talked about. Now, going on to ideal increase in pressure head in the impeller. So we'll consider a case of an ideal impeller in which there are no losses. The inflow is assumed to be radial, which would mean the world velocity will be 0 and V1 will be equal to Vf1. The energy balance between the inlet and the outlet of the impeller can be written per unit weight as follows. So that will be energy of the liquid at inlet plus the energy added externally by the pump to the liquid, that will be equal to the energy of liquid at outlet. So the formula given in Bernoulli's theorem's form will be as follows: rho1 by gamma plus z1 plus v1 square by 2g plus vu2 u2 by g is equal to rho2 by gamma plus z2 plus v2 square by 2g. And the piezometric difference will be written as del hp is equal to hn, which will be equal to he minus the change in kinetic energy. So for ideal conditions, the piezometric difference is also given over here. So energy losses in the impeller. So the first one is hydraulic loss. The hydraulic losses stem from the following. First is circulatory flow, that is HC at the passages of the impeller. This component of the hydraulic losses is particularly independent of the discharge. The fluid friction at the flow passages, that is HFP. This loss depends on the area in contact with the fluid flow and the roughness magnitude of the surface. The third one is the shock losses at the entrance of the impeller HQ. So this loss occurs due to improper entry angle of the flow with respect to the blade angle, that is alpha, and beta. Blade angle will be beta here. At design conditions, this loss is particularly zero and increases at reduced or increased flow with normal modes. Now next is the non-hydraulic losses, that is leakage loss. First one is leakage loss, that is due to the improper clearances between the impeller and the casing. The some motor, after receiving the energy at the impeller, may not exit from the front of the pump outlet. The next one is mechanical losses. These include mechanical losses due to the friction at bearing and packings. Also, the friction loss due to interaction of the rotating impeller shaft with the fluid surrounding it, called this friction force, is considered as mechanical friction. So now moving on to the efficiencies. So first we'll consider a pump unit with manometric head HM and the outlet discharge Q. The power supplied to the shaft from the prime mover is P. First, volumetric efficiency. So generally it is possible that out of a total discharge of water discharged by the pump, some quantity of discharge QL might not have been delivered at the discharge end of the pump due to the leaks in the clearances between the impellers and casing, as we saw before. So these leaks ages include those that flow back to the suction side and those that go to the waste outside the casing. So therefore, the volumetric efficiency of the pump is defined as discharge reaching the pump outlet divided by discharge entering the eye of the impeller. That is Q by Q plus QL. Now going on to manometric efficiency, while the theoretical head, Euler head, that should have been developed by the pump is HE, the actual manometric head developed is less than HE by an amount of HFI, as we saw before. So these losses include the frictional losses in the blade passage. This is all we have talked about before. And now the manometric efficiency is also defined as the ratio of manometric head developed by the pump to the head imparted by the impeller to the liquid in the pump. That is also equal to Hn by He, which is also equal to GHm by Vu to U2. Now, going on to mechanical efficiency. In a pump, there are inevitable mechanical frictions that occur, and due to this, the power transmitted to the liquid by the impeller is smaller than the power supplied to the shaft by the prime mover. Here, the mechanical efficiency is equal to the power actually delivered by the impeller divided by power supplied to the shaft. That is equal to the Euler head He divided by Euler head plus the mechanical efficiency. By the mechanical head, no, sorry. So now the fourth one is the overall efficiency. The overall efficiency, also known as the total efficiency of the pump, is defined as the ratio of actual power output from the pump to the flow to the power supplied by prime mover to the shaft. That is equal to power output from the pump divided by power supplied by the prime mover to the shaft. That is equal to gamma into Q into Hm divided by P, that is the pressure. So the total efficiency can also be written as total efficiency is equal to the multiplication of mechanical efficiency, the manometric efficiency, and the volumetric efficiency. So now Saurabh will discuss about the characteristics of centrifugal pumps and the affinity laws.
My name is Saurabh Solkar and my roll number is 276. My topic is characteristics of centrifugal pump and affinities law for centrifugal pumps. Characteristic of centrifugal pump is basically the interaction of two variables which are head and flow rate. It describes its performance. For preparing main characteristics charts, data obtained for a specific pump having fixed geometry is plotted with the head, power, and efficiency as ordinates and discharge as a common abscissa, with speed as third variable. The graph for the characteristics for uh, main characteristics, uh, ice operating characteristics and other characteristics are given here. And for preparing main characteristic, as I said, for a specific pump having fixed geometry, head power and efficiency as ordinate and discharge as a common abscissa are plotted. For manufacturing purposes, the size of the impeller is taken as a third variable instead of speed variable. The point at which the efficiency reaches the maximum is known as best efficiency point. Main characteristic can be combined to produce HQ curves for different speeds with ISO efficiency curves. HQ curves means basically the head and flow rate curve. By considering a horizontal line representing a known efficiency value eta naught 1, this line gives discharge corresponding to different speeds having the designated efficiency. Operating characteristics of a pump are the constant speed characteristics of a given type of a pump of fixed geometry. This is essentially the set of curves consisting of head and flow rate curve, power and flow rate curve, and efficiency and flow rate curve, all belonging to a prefixed value of speed n, all extracted from the main characteristics curve. It often comes as surprise that pump flow and pump head can be related, however, each pump has its own characteristics and the relation is different for different pumps. The characters let's look at a simple way of describing this. If the hose is lifted high above the pump position H1, then very little flow Q1 is will drip out its end. Position H0 has a special term. It is called the shut-off head or closed valve head. If the hose is now lowered a little to position Hi, more flow comes out of the pipe Q2. This process can then be repeated at several heads Hx and associated flows Qx measured. The characteristic obtained in this way is called flow head characteristic of a centrifugal pump. The pump can operate at any points lying on it. Different head values corresponding to different flows. As a rule, with increasing head decreases flow and vice versa. As the flow increases, the pressure decreases. Now we will talk about what determines the head of the pump. The larger the impeller diameter, the higher the fluid velocity, the higher the pump head, as we can see in this uh, picture also, in diagram also. And what determines the flow rate of the pump? The wider the impeller channel, the more liquid passes through the impeller, more pump flow. The demonstration is given here. Pump operating range. Well, manufacturing companies define some pump operating range. The pump can operate at any point of the curve from zero flow up to maximum, but pump manufacturers limit the minimum and maximum flow, and the reason behind it, the allowable operating range of the pumps must be between 70% and 120% of the flow, corresponding to the maximum efficiency of the pump. In the manufacturing catalog at the beginning, we can see the field of characteristic of the entire standard hydraulic range or family range, which consists of the hydraulic ranges or of pump models. The reason for this range is based on the physics of the design. Operation in this zone ensures the highest efficiencies and the most reliable operation with the lowest bearing loads, turbulence, and vibration. In the pump case, the impellers of different diameters can be installed. Depending on the diameter, the pump head also changes and we receive different flow head characteristics. Each field is limited by the left and right borders of the allowable operating range and by the maximum and minimum impeller diameters. The power characteristic shows how the power absorbed by the pump changes uh, depending on the flow. A good estimate of power can be developed if the motor efficiency at the different load condition is known. In most cases, the pump power increases as the flow increases. More power is needed to pump more fluid, but this is not always fair. There are cases when the power characteristic may, upon reaching a certain value, with a further increase in feed, decrease. These are the two demonstration of rising characteristic and non-rising characteristic. In the case of rising characteristic, the selection of power electric motor should be more careful because it can risk of the motor overloading. while in case of non-rising characteristic, there is no risk of motor overloading. And these four are the graph. The steepness of the curves plays an important role in the selection of the pumps, methods of pump control, influence on pump parameters after wearing. In these four graphs, the steepness of uh, the graph, that is head and flow rate characteristics and power characteristics, are connected. We can look at these pictures. QH has a less steepness, flat power, has a rising shape. While in the second picture, QH has more steepness, power, has not rising shape. Pump efficiency characteristics. This representation is convenient from the point of view of impact analysis impeller diameter. With a decrease in diameter, the efficiency of the pump decreases slightly. Now we will talk about the affinity law. Turbo-machine affinity loss can be used to calculate volume capacity, head or power consumption in centrifugal pumps when the changing speed of wheel diameters. The affinity laws of centrifugal pumps of fans indicates the influence on volume capacity, head, while that is called also called pressure, and or power consumption of a pump or fan due to change in speed of wheel revolution per minute, that is RPM, geometrically similarity, change in impeller diameter, and there are two sets of affinities law for a specific centrifugal pump and family of geometrically similar centrifugal pump. These three are the affinity laws: the volume capacity, the equation as given, and the corresponding values are given. Like the variable, what variable will describe what quantity, what what feature. Like Q is volume flow capacity and N is wheel velocity. Similarly, we have the equation for head or pressure and power as well. Now we are talking about the two sets of affinity as the specific for the specific is centrifugal pump. If wheel diameter is constant, then the corresponding equation of affinity law will change like this. The Q1 by Q2 will be equal to N1 by N2, and similarly for head pressure or head or pressure and as well as power. And second set was if we change the impeller diameter, then the corresponding equation will change like this, and the graph is given for for the same impeller diameter for changing in the impeller diameter. Now my partner Siddharth Sahu will continue with the cavitation part.
My name is Siddharth Sahu and my roll number is 2K20ME271 and I will be explaining the topic of cavitation. We all know that cavitation is a major problem with centrifugal pumps, but what exactly is cavitation? When when the absolute local pressure at any point in the conduit carrying the liquid approaches the vapor pressure of the liquid, the dissolved gases and liquid vapor come out of the liquid as bubbles. These bubbles strike the surface of the tube and damage it. This phenomenon of formation, travel, and collapse of vapor pressure is known as cavitation. NPSH or net positive suction head is the pressure required at the pump inlet to make the liquid flow through the suction side without cavitation. The quantity that is used to determine whether the local pressure inside the pump is adequate with respect to pressure of the flowing fluid without causing cavitation is termed as NPSH or net positive suction head. Uh, in this figure, we can see the damage caused by cavitation to a centrifugal pump. And now there are two types of NPSH, NPSH available and NPSH required. NPSH available is the difference between the pressure at the suction of the pump and the saturation pressure of the fluid that is being pumped. And NPSH required is the minimum NPSH required to prevent cavitation in the pump. NPSH available is calculated with the help of this formula, and NPSH required is provided by the pump manufacturer, and it is required to ensure and it is our duty to ensure that NPSHA is available NPSHA uh, available is sufficient to cover it. In this graph we can see there are two regions. The first one is of no cavitation and the second one is of cavitation. We can see that as the volume flow rate increases, the NPSH available decreases. This is because of frictional and other types of losses, and consequently, as NPSH available increases, the NPSH required, uh, and as NPSH available decreases, the NPSH required increases. We can see that there is a point of intersection of NPSH available and NPSH required. This is the point of maximum flow rate, beyond which there is cavitation. Now we come to the impacts of cavitation. The first impact is of performance impairment, which means reduction of head and efficiency. The second one is mechanical damage, which is reduction in useful life of the centrifugal pump. The third is noise. Cavitation noise is a typical crackling sound as if gravel is being pumped along with water. The next issue, the next impact is pressure pulsation. Pressure pulsation is the torque fluctuation and vibration of casing and bearing house. The next one is vapor lock, which is a situation in which impeller is trying to operate with the fluid that is very much lighter due to the presence of vapor bubbles. This results in complete loss of generation of head. Here is a short video in which we can see the noise effect of cavitation.
Here we go, closing the valve. And watching the gauge.
Water is being passed through
Gauge
this
will go
pipe
down.
and the pressure inside the pipe is being lowered
Minus
gradually.
10 inches of mercury. Minus 12.
We can hear
Minus
the
14.
noise
You
of
can
the
start to hear flashing occur there.
noise of the water bubbles increasing.
16. More
It's
noise.
almost as if there are solid rock particles inside this
Minus
tube.
18. Minus 20. You start to hear that sound. That sounds almost like
The
rocks
sound
going through the
increases
pipe.
as the pressure is
There's
being
no
lowered.
debris. There's no solid material through here. That
Now, uh, a natural thing which comes to mind is how to prevent cavitation. So, to prevent cavitation, there is a general rule. Centrifugal pumps located less than 4 meters above the water level should not experience cavitation. We can minimize the number of valves and bends in the suction line. We can use eccentric reducers, not concentric. We can ensure that the straight side of the eccentric reducer is installed along the top of the suction line. Suction length should be as short as possible. We can increase the size of valves and the pipe work. Suction pipe should be at least the same diameter as the pump inlet connection. Now we have finished the topic of cavitation, and we come to the effects of viscosity on on the performance of a centrifugal pump. We can see a graph, and to understand this graph we have to know what is mu r. Mu r is the ratio of the dynamic viscosity of the liquid with respect to dynamic viscosity of water. uh, Liquids with who have which have viscosity less than that or equal to water. um, in liquids which have viscosity less than that or equal to water, we can see that there is no change in no or negligible change in the characteristics of the pump. However, when more viscous fluids are used, the nature of flow changes. We can see that as mu r varies from 1 to 10, there is only a marginal change in the properties of the pump. But after mu r reaches 10, there is a dramatic change with considerably large reduction in the value of head for a given discharge and large increase in the brake power with discharge. Now I would like to invite Somnath to continue.
I am Somnath. My roll number is 2K20 ME273. I am going to discuss about variant of centrifugal pumps. In these points are single suction pump, double suction pumps, multi-stage pumps. mixed flow pumps. Now I am starting from single suction pump. Single suction pump, it is also known as end stage pumps or single stage pumps. In these pumps, only single impeller in which high flow rate and diffusers for pressurized inflows. Impeller of the pumps is connected with a shaft by driven engine or electric motor. It can lift water 125 meter up to, and then when the pump start, the pump shaft drive the impeller for high speed rotary motion, forcing the filling fluid between blades to rotate with the effect of inertia shear centrifugal force. The fluid moves along the radial direction from the impeller center to the peripheral region where the fluid obtains the energy in the moment through the impeller. Yeah. And we have some advantages. It has a simple structure. It has a stable performance. This pump has high speed, small volume, large flow, high efficiency, long services life, and applications, sewage technology, cleaning technology, energy technology. And next slide is when fluid when fluid from the impeller is pushed toward to the peripheral directions at the same time, low pressures areas is formed in the center of impeller. Double suction pump. This type of pumps impeller actually consists of two back-to-back impeller from which the water flow into a volute. Double suction pumps works just like two same diameter and suction pumps work at the same times. Meanwhile, the entry and exit end of the double suction pumps are in the same direction, being perpendicular to the pump shaft, which is helpful for the layout and installations of pumps and water pipes. It is widely used for the fluid delivery in drainage and irrigation of farmland, waterworks, pump stations, power stations, chemical industry, mining, firefighting, and shipping. And next slide is multi multi-stage centrifugal pump. A multi-stage pump is a type of pump which contains two or more impellers which may be of the same or different types. Examples: low NPS impeller, double suction impellers, and both pump have different suction pipe but same discharge pipeline. Both pumps have their own motors. Discharge volume increase Q1 plus Q2 while head remains constant. If we required increase, we require volume increase or discharge increase, then add the two motors. Next slide is horizontal multi-stage centrifugal pumps. This type of pumps has a segmented casing with modular interstage components. The rotating assembly is held between bearing housing, make the assembly more balanced for high pressures. The horizontal configuration of multi-stage pump is best applied in application like reverse osmosis, boiler feeds, shower. Vertically multi-stage centrifugal vertical multi-stage centrifugal pumps have a vertical shaft where stages are stacked one on the top of the next. Vertically multi-stage pumps are great for areas and motor combo is also cleanliness are small in these pumps. Therefore, clean water application are best for this pump. High pressure shower systems, boiler feed water don't have pressures output with a single. And next slide is mixed flow pumps. We will we will discuss about mixed flow pump. Mixed flow pumps are centrifugal pumps that have a mixed flow impeller added to them. The fluid flow within these pumps is pumped both axially and radially. Mixed flow pumps are centrifugal pumps that perform the same primary purpose. To put it another way, they work by sucking air through a rotating impeller due to the centrifugal force caused by the impeller after the fluid is sucked in it. It is pushed out toward the outlet. Now discuss about working. When the impeller is rotated by the power machinery, the blades push the water body on the one hand while also rotating the water body to produce centrifugal action on the other. Under the effect of the thrust and centrifugal force of the blades, the water body produces flow and uh, builds pressures. It is frequently utilized when considerable conveying displacement and mild pressures are required. It is a specific speed in low RPM like 35 and 80 RPM and the specific speed in high RPM 80 and 160 RPM. Mixed flow pumps cover the transition range between radial flow pump and auxiliary flow pump. Thank you.
I am Saurabh Barwal. I continue this presentation with my topic axial flow pump. Here I first start with the introduction of the axial flow pump. Axial flow pump is the dynamic pump which has suction parallel to the impeller direction. It does not change the flow direction of the fluid. The pump, the fluid enters and exits in the pump in, in parallel direction to the impeller. The impeller inside the pump. This pump has 3 or 4 blades that are installed on the impeller. The pump blade designed in such a way that pump discharge the water axially in the parallel direction to the impeller, not perpendicular. The parallel alignment of the impeller blades creates a very low pressure when pumping water. These pumps used for high flow rate, low pressure application. These dynamic pumps can generate high flow rates up to 100 of 1000 of gallons per minute. It is also called propeller pump because the axial impeller is similar to the propeller. Now I start the working principle of the axial flow pump. In axial flow pump, the impeller blades guide the fluid axially. In this pump, the pressure is generated by the directing the liquid to the impeller blades. In this dynamic pump, the impeller blades have an airfoil that allows the fluid to flow and generate pressure. The liquid is pushed towards the rotation of the impeller. That is, fluid particles do not change their radial position as they flow through the pump. As a result, the liquid can flow axially into the impeller and exit liquid almost axially. The propeller of these dynamic pumps are driven by electric motors. The required power increases as the flow rate decreases and the maximum power can are obtained at zero flow rate. Uh, the power requirement and the pump heads also increase with tilt, adapting the pump to system condition for the most efficient operation. Here are the some applications of the axial flow pumps: lift irrigation, land drainage, flood water management, coffee dams, river intake, water treatment, blast control in marine. Here's the graph. Here I show the graph which shows the performance characteristics of the axial flow pump. Here, this graph is basically the best percentage of the axial flow pump. At the 250% of the head, uh, at the 250% of the head, the axial flow pump is basically shut off. As we increasing the discharge, the head is decreasing as we increasing the discharge. 60 to 120% is the confined state and the stable state of the axial flow pump. But we can conclude to this graph as we increasing the load, the axial flow pump is unstable. Now I compare the performance of the axial and the radial flow pumps with few characteristics. Specific speed. Specific speed of the axial flow pump is more greater than the radial flow pump, and mechanical loss in the pump is negligible in the axial flow pump, and the radial flow pump is significant. Intake design is very important in the axial flow pump and moderately important in the radial flow pump. Net positive suction head is high in axial flow pump and the low is the radial flow pump. Air handling is good in axial flow pump and the poor in the radial flow pump. Flow reverse in the axial flow pump. Water and the flow is the same direction as before in the radial flow pump. HQ curve is steep in the axial flow pump and the flat to moderately steep in the radial flow pump. And the ratio of the safety of the operation head to the normal head is 2 to 3 point and 1.1 to 1.6 in the radial flow pump. And the ratio safety operation power to the normal power in axial flow pump is 1.5 to 2.5, and in the radial flow pump is less than 1.0. Thank you so much.
My name is Siddharth Kumar Jha and my roll number is 2K20ME270. My topic is matching of pump characteristics with system characteristics. So, pump characteristic can be defined as the relationship between the net head produced by the pump and the flow rate at a given rotational speed of the pump. A typical HQ relation of a radial flow pump with the head is plotted on the vertical axis and discharge Q is plotted on the horizontal axis as shown in the figure. This curve is known as pump characteristic curve and is popularly called as the HQ curve. This plot of efficiency against discharge is known as efficiency curve of the pump. Here, the highest efficiency point is the best efficiency point, which is extended to the HQ curve, intersects at the point B, which is the designed operating point of the pump. But this operating point is not the actual operating point. The actual operating point is obtained when the system is also considered. So the operating point depends not only on the pump characteristic but also on the system characteristic. Now, system means suction line and the delivery line. Here, the system characteristic is based on two basic components: static head and dynamic head loss. Static head is the difference between the elevation of the tank B and the tank A, which is ZB minus ZA in this case. Sometimes the tanks can be pressurized, and so the piezometric head of the two reservoirs is taken. The difference of the piezometric head gives us the net head, which is given by the expression shown in the figure. Now, moving on to the next, dynamic head loss. Dynamic head loss represents the head energy loss due to friction. And this is also of two types, which is frictional head loss in the piping and the energy loss due to the valves. Total pipe frictional loss can be given by the formula FI square upon 2GD, where Fi is the Tracy friction factor. Similarly, the total minor losses due to the walls can be given by KI square upon 2G. Now, so this definition sketch of system curve shows that the static head is constantly being applied while the discharge increases, while the dynamic head increases as the discharge increases. This is due to the factor that dynamic head is a function of discharge. Now, how dynamic head is a function of discharge? Now, dynamic head we know is directly proportional to Vi square. Now, Vi square is velocity in the pipe. That can be in the section pipe as well as in the delivery pipe. So, the velocity, we also know that the velocity is proportional to the discharge. So, from that relation, H dynamic is directly proportional to Q square. So the total system head loss is the sum of the static head loss and the dynamic head loss and is given by the equation 5.74. Moving on to the next topic, the matching. The matching of the pump and the system characteristics. Both the system characteristic and the pump characteristic have been plotted here. This is the system characteristic which can also be seen as a resisting head, and this is the pump characteristic. The intersection point between the system characteristic and the pump characteristic, that is the best efficiency point, BEP, is obtained from this figure. This is not equal to the the designed best design point for the pump, but it is slightly different due to the system curve and the losses made by the system curve in the pipes. So, in actual pump installation, the system curve is based on estimated values of various coefficients. Exact coincidence of point A and the location of BP is just fruititious. In reality, one should be looking for best operating range. Disclaimer: the snips here are taken from Hydraulic Machines book by K. Subram. Thank you.